Hi, I'm Amir Hossein Mirza Bozorg, and in this video, I'm gonna talk about Comprehensive Abaqus Package Chapter 15, Linear and Nonlinear Vibration. How to ask your video-related questions. Don't hesitate to ask any questions you might have about the explanations presented in this video using the comments below. We will try to answer all questions regarding the video details in the comments below. New Abaqus users who want to develop their modeling skills faster in their projects can request user-oriented online and offline services. Subsequently, we offer step-by-step guidance, tutoring, and consultancy regarding their problems. The online service includes online sessions, and the offline service includes creating special tutorials. In addition, a combination of the two can be requested. This is the table of content for Chapter 15. Okay, I want to start chapter 15. It is about vibration analysis, linear and nonlinear vibration analysis. First, I want to talk about linear frequency analysis. Linear frequency analysis. Okay. Okay. First of all, let me talk about vibration. What is vibration? Suppose that we have a spring, and here we have a mass. And then the stiffness of the spring is K, and the mass moves forward and backward. If I want to write the governing equation of this system, suppose that this is the equilibrium point, and this is x, and then this distance is x. The force is applied to the mass from the spring is kx. Okay, so I write sigma f is equal to ma. Sigma f is minus kx. Why? Because it is in the negative direction. Is equal to mx double dot. So we have this equation. And the answer to this question, to this equation, is That's it. And according to the initial conditions, we can find A and B, and omega is equal to this. This is the frequency, and this is vibration. This is vibration analysis, and also this is here we have a lumped mass. This is a concentrated mass or lumped mass. But for example, for a beam, it is not lumped. It is distributed, and a distributed system has infinite number of frequencies, and we use numerical simulation to find these frequencies. And yes, so I start my slides, and also I open Abaqus. In this chapter, the natural frequencies of a single-ended beam single-ended beam are calculated using the frequency step. I think I must change this word, single-ended. One of the sides is fixed. Single-ended beam are calculated using the frequency step, and the result of the numerical solution based on Abaqus is compared and discussed with the analytical solution. The cross-section dimensions of the investigated beam are 0.01 and 0.02 meters, and it has a length of 1 meter. We will create 4 models. In model 1, the modeling space is 2D, and we use beam elements. In model 2, the modeling space is 2D, and we use shell elements. In model 3, the modeling space is 3D, and we use beam elements again. And in model 4, the modeling space is 3D, and we use solid elements. And we will compare these results with the analytical result. First of all, I create model 1. It's a beam, 2D planar, deformable, wire. I set the approximate size to 4. I create the origin, and I fix it. This length is 1. I go to the property. I define the material. It is created from steel. Sorry. And also beam section. I define beam profile, rectangular beam profile. A is 0.02, B is 0.01. Also, I must assign it to the geometry, and I define the directions. I go to the assembly, and I go to the step, and I create job 1, and I run it. Okay, as you can see, the simulation is completed, and it's because it was a very simple simulation, and you can see that here the time increment size is 10 to the power of minus 36, and even we had this value for the buckling analysis. And in chapter 10 I told you that I will tell you about it in other chapters, and now I want to tell you about it. If another general step follows a perturbation step, Abaqus standard uses the state of the model at the end of the last general step as its starting point, not the state of the model at the end of the perturbation step. Thus, the response from a linear perturbation step has no permanent effect on the simulation. Therefore, Abaqus standard does not include the step time of linear perturbation steps in the total time for the analysis. In fact, what Abaqus standard actually does is to define the step time of a perturbation step to be very small, 10 to the power of minus 36, so that it has no effect when it is added to the total accumulated time. The exception to this rule is the modal dynamics procedure, and we will use modal dynamics procedure in the next simulations. So as we don't want the other steps to be affected by the frequency step, so the time increment size is set to 10 to the power of minus 36. And let me show you the results. You can see modes. Also, we have them here. This frequency is in hertz. Cycles per time, it is in hertz. This is the first one, second one, third one, fourth one, fifth one, sixth one, seventh, eighth. See the eighth one, it is longitudinal. The others are transverse. If you are in the 2D space, you can only calculate the longitudinal ones and the transverse ones. You cannot calculate the torsional ones. But in the 3D space, we can also calculate the torsional modes, so it's more complete. And here you can see, if you see our element size is not good for modes for 9th, 10th, and other modes. If you see, this mesh is coarse for higher frequency modes. So until the 8th, it's good. Okay, until the 8th mode. And also, if you see here, here they have set the deformation scale factor to 0.1. If I set it to 1, it is the correct one. But for better visualization, usually Abaqus uses a coefficient less than 1. And in the second model, I will use shell elements to do the analysis. So I go back, I create model 2. In model 2, I create beam again. It is 2D planar, deformable, shell. So here I create 4 viewports. job 1, job 2, job 3, and also job 4. Okay. Very good. Please see the natural frequencies. 8.17, 8.44, 8.17, 8.07. You can see that they are very close to each other. I go to the next one. These two ones, the second mode shape is in the XZ plane. So I go to the other one. 51.07, 52.78, 51.072, and 50.57. Also, you can see that they are close, and these ones are always the same. Why? Because both of them use beam elements. I go to the next one. This is also in the XZ, so please check them yourself. The error of this one is always more than this one. I don't know what is the cause of this. I don't know, but you can check it from the results. I don't know what is the cause of it. Yes. Their modes are the same, and also their modes are the same. Why? Because they are in 2D and they are in 3D. And please compare the frequencies. Very good. And here we have all of them together. Now I want to calculate the natural frequencies using the analytical solutions. This table is for the longitudinal mode shapes, and we have this one. One side is fixed, one side is free. And the natural frequency is this. Okay? And I have calculated it. It is 1265.924 Hertz. And I think it was the, yeah, 8th one. Why in this case it is 9th? Also I think it is 14, so here I must find 14, 15. Okay, you can see also 1265.924 1265.6, 1265.6, 1266.5, and 1327.4. You can see that these three ones are very close to the analytical solution. Also, this one, it doesn't have much error. Let me calculate its error. Only 5%, less than 5%. It's acceptable. Based on the results obtained from Model 1 and 2, the first modes of longitudinal vibrations are the 8th and 9th modes, whose natural frequencies are calculated as these values. Okay? Respectively, comparing the results shows that there is an acceptable agreement between the numerical and analytical solution in estimating the first frequency of longitudinal vibration. And now I want to compare the transverse ones. And here you can see the formula for calculating the transverse natural frequencies. And the first transverse mode, its frequency is 8.18, the other one 51.26, the other one 143, and the other one 281. Very good. So I set it to 8.17, 8.18, 8.44, 8.17, 8.07. $51.26, 51, 52.78, 51, 50.57. Omega 3. $143.53, 142.69, 137.5, 142.69, 141.51. It's accurate. $281.28, 279, 288, 279, 277. So it means that our simulation is correct. In both longitudinal and transverse vibration modes, the natural frequencies obtained from Abaqus agreed with those obtained from the analytical solution. In the meantime, the similarity between the analytical solution and the solution based on the two-dimensional beam element was more due to the affinity of the theory used in the analytical solution and the internal formulation of the two-dimensional beam elements. That's it. Do you have any other questions? Because you are very quiet. Okay, no problem. What's the time? I want to give you a break for 15 minutes. Then please go back after 15 minutes. We only have a few simulations to do. A small part of the class is remaining, and then also chapter 15 will be finished, and then in the next week we work on chapter 16 and a small part, a very small part of chapter 11. So please go for a break and go back. Then we compare the result of this simulation with the result of the previous simulation. The first step is completed. Now we have the second step, and then the simulation is finished. Please compare them. You can see that here we have difference. And I go to the next one. Also, you can see the difference. As the value of force is not too large, so the difference is not too much. If it is increased, and for example the material and also we define plasticity, and the material undergoes plastic deformation, then the difference will increase. Okay, the difference will increase, and but in a lot of cases the difference is sensible. Okay, here it is not very large. This is the concept of nonlinear vibration analysis. For example, if you want to do nonlinear analysis, nonlinear vibration analysis on a bolt connection, in the first step you must apply bolt loads. In the second step you must fix the length or adjust the length. I have forgotten what was in Abaqus. I told you in chapter 9 in the bolt connection analysis. And then in the third step, you must define frequency step. And then you can do the nonlinear frequency analysis. It was the concept of it. As you can see, it is very easy. So this part is completed. And then I go for the linear dynamic analysis. Linear dynamic analysis. We can do linear dynamic analysis using linear perturbation steps or using general steps. Let me tell you about linear dynamic analysis. In chapter 11, in chapter 7, we did a simulation for a structure. It was a plate with stiffeners, and a blast load was applied to the plate. And we used dynamic explicit step, and we defined plasticity, and also energy was set to on. It was a nonlinear dynamic analysis. Also, in chapter 11, we defined, we created a model for high velocity impact, and there was an impact between impactor and the plate. And also it is a nonlinear dynamic analysis. But when we have none of the sources of nonlinearity in the simulation, then it is a linear dynamic analysis. And you can use linear perturbation steps, and in this case I want to use modal dynamics step. Also, we have some other steps for doing linear dynamic analysis using linear perturbation steps. And also you can use general steps like dynamic implicit and dynamic explicit. But if you simulate the problem using these steps, it takes more time than this one, because uh, uh, they are very powerful and they are better for nonlinear analysis. Okay, for linear analysis, as it is very simple, you can also use this one. Okay, here I create a copy from model 1. I name it model 1 explicit. And even here we can use its results. Uh, and very good. You can see that they are totally the same. They are totally the same. Very good. I kill it. I run this one. I think the result is ready before it is. It's very interesting. I told you that it doesn't solve it. It is only something. I don't know. It's very interesting. Let me check the result. U2 model 2. Yes, it doesn't solve it. I mean, the history output is ready. I told you why. Here you can see the resonance. For example, in this point, the beam must break. It must break. But we didn't define it. So it doesn't break, and only the displacement of the beam increases. Its amplitude increases due to the resonance. And you can see it. And for the job 2 model, why it doesn't? Aha. Huh. Eh? you can see the amplitude is decreasing because we are going back. Okay, we are going back. Yes, that's it. So we could model resonance, and you can see that here the theory works. And yes, that's it. Do you have any other question or any other questions?
No.
Uh-huh.
Thank you.
You are welcome. So chapter 15 is finished. Next week we go for concrete analysis, and it is the last chapter, and the course will finish. And thank you so much for your participation in every session of the course. How to purchase packages or individual chapters. Each of the packages and individual chapters includes CAE, JNL, and IMP files, step-by-step tutorials with detailed explanations and investigation of the results, slides and reference papers, and standards. Packages specifications and payment details are provided in the video description. Also, you can pay the cost of the packages in 2, 3, or 4 installments according to your budget or income. In the future, updates will be provided for free for everybody who purchases each chapter or each package. The cost of each chapter or package will increase after each update for new buyers, but those who purchase the package would have endless access to all the upcoming updates. This will make the content up to date for new needs and new problems which must be solved via FE simulation. You can contact us using Telegram or WhatsApp, or you can send email to us. We can have one-on-one tutoring on the AnyDesk WhatsApp, and we can make special tutorials to your order. We can conduct high-quality simulations for your thesis, exercises, and industrial projects. And we offer support in writing the modeling and result discussion part of your thesis. And we have consulting services for MSc, PhD positions or job interviews. And we can help you to prepare the presentation of your simulation works. Now I want to suggest you several related videos of our YouTube channel. Thank you so much for watching this video. Have a good time. Goodbye.